So the plan for today is just to do a quick review and sort of just point out in the notes, the couple, the what I feel are the high points that you should have a good handle on. Also to take any questions that you guys have. What's that? I said also to take any questions that you guys have, and right, there is a mock exam up on Carmen. Now, just the word, so I essentially wrote enough questions for 2 exams, right? And then randomly selected which ones. The questions on Carmen, though, since I had to put them up earlier, haven't been gone through several times by me for clarity, right? So I just sort of wrote the question down and then put it up on the mock exam because I wanted to make sure you guys had it up in plenty of time. So I just wanted to make the point that the real exam is sort of being filtered through a couple other people and make sure that it's understandable, right? Everything is as clear as humanly possible. Okay, so just real fast, sort of the high points of aluminum, right? The common alloying elements, right? And notice that the solubilities, right? And the max solubility, right, are sort of in this, well, what are the consequences of these solubilities, right? The consequences are that our choices for alloying are fairly limited, right? We don't have a huge amount of elements that we can select, so that leads to some general classes, and that we get a lot of precipitation, right? Small concentrations give us secondary phase formation, right? And generally the general trend is GP zones, intermediate phases with an increasing solvus, right? So how come the easiest phases to precipitate also have the lowest solvus? Think about it from thermodynamics.
A more stable phase would readily precipitate at a lower aging temperature.
Well, it's the same reason as sort of why we have the precipitation sequence, right? It's because the GP zones have a much more similar structure, right? They're FCC, they're coherent, right? So it doesn't, and they have a fairly low free energy, give you a very low free energy change, right? So if you add enough energy, right, enough thermal energy, the increased entropic term, right, is going to lead you to dissolve, right? You need fairly low temperatures for the GP zones to be stable. Okay, so basically, this is an important picture to understand, right? What are you going to do if you change your surface energy, right? And your surface energy goes higher, what happens? Your delta G star gets higher, and your stable nucleus size gets larger, right? The bulk free energy term right? This is your degree of undercooling, and then this is a small correction due to the volumetric strain associated with the particle, right? So understand the general picture, right? And that for nucleation rate, we have a driving force limited term, right? How much of an, right? This is the degree of undercooling, right? The larger this becomes, the higher our driving force comes, but if we lower the temperature too much, we don't have sufficient mobility, right? So that gives us a maximum of the nucleation rate at some undercooling. Right. General GP zones, directions, right? Why does aluminum copper give you platelets? Right. So basically understanding this figure, notice this was a question on the mock exam, right? And so being that I divvied things up randomly, right, it could have very well been a question on the real exam, right? So understanding what's happening inside of the microstructure, right? So I think that's going to be a general clue, right? If I show you a figure like this, right, tie your answer back to what's going on in the microstructure, right? Well, we know aluminum copper, our primary reinforcing phase at peak age at these temperatures is going to be theta double prime, right? So here's GP zone formation. GP zones have saturated, formation of double prime, they're growing, particles are getting at the same volume fraction, the particles are going farther apart, peak aged, right? This is where it's equally hard to loop around and to cut the particles.
Why with 2 and 3% copper you just have one slope? Is it because you're fully within the theta double prime region?
Well, so 2%, you don't basically, right, what is the GP zone? Right, it's just a collection of copper, right? When you're at a dilute or more dilute concentration, right? Remember, so it's the concentration, the spacing between the copper atoms, right, is proportional to the volume, right? Right. So you've got a much larger, right? It's just you're just in a more dilute system, so it takes longer for everything to come together.
Why is that dotted line?
I'd have to go back to the actual source.
And for the curves below, like 3% copper.
Yeah.
Why did the slope like? What was that?
So my guess here is these are different experiments, right, that have been combined together to make one curve, right? So, but the question about 3%, why is it? Well, I mean, so if you extrapolate this back to 0 time, right, that's the as quenched, right? And then you've got a slow growth of GP zones followed by nucleation of your theta double prime phase at the GP zone concentration.
So that doesn't show the saturation.
No, because you just, right, the kinetics of it, it's hard to say exactly without looking at pictures of each of these, right? The main thing is, right, what's the main general trend here, right? So just think about this, the 4%, right? In general, the general idea is you're going to have GP zones followed by the other phases of interest, right? And that if you get a nice dispersion of GP zones, those are natural places for your intermediate phases to grow, right? I don't want to speculate, right, and say exactly what's happening. I haven't looked at enough micrographs of low concentration counters. I'll say something stupid if I just open my mouth. Yeah.
The practice example, so SS to assess what the microstructure is like in the condition.
Yeah.
That different from the condition.
It's just that your particles are growing by Oswald ripening, right? And so they're getting farther apart. So that means it's easier to bow dislocations. Right. So then this is basic strengthening mechanisms of cutting, right? All right, that when the particles are really close, the dislocation can't bend around them because of the line tension, right? So, and GP zones being coherent, right? It's more instructive to think of them as sort of strained regions rather than actual sort of particles, right? As they grow, the distance between them becomes much larger than the strain field, and now the dislocation can easily bend around them. Okay, so as you slip, you cut these particles. Eventually, you can make them, right, especially if you're in a fatigue situation where we're ratcheting, we're going back and forth, but there's a small net in one direction relative to the other. Eventually, these particles are going to be sheared completely in half, right? And if this particle is close to our star, if you cut it in half, right, the volume becomes small enough that we now will dissolve. Right. Looping, right? If you make sketches on the exam, put a sign on your dislocations so it's easy to see, right, what's positive and what's negative sense, right? And remember that when you loop, you have your dislocation loopers left behind, so that each dislocation gives you a slightly narrower channel width behind it, and you have pile-up type behavior. Peak aged versus under and over aged. Right. Understanding that even though, right, the free energy of the GP zones themselves is higher overall at a given concentration from the common tangent construction, you have right, you've got a net lowering of free energy, right? And the driving force for nucleation is the tangent at this point up. This is your chemical, this up here, right? If I take a tangent here, this is my chemical potential of aluminum in alpha. My chemical potential of copper in alpha would be up here. And since the first nucleation event doesn't actually change my overall composition, my driving force for nucleation will be this difference here. Right. Okay, you don't have to memorize any of the structures that I talked about, but the general trend that you go from more similar to most dissimilar and more coherent to less coherent interfacial energies as you go up the precipitation sequence, right? And this image here showing the overall change in free energy as you go from one phase to the other, but also the change in composition of the alpha phase and of the particles, right? And that how that going in sequence gives us a small nucleation activation energy for each one, compared to a very large activation energy for going right from alpha to the thermodynamic phase, right? We need vacancies because that gives us enhanced mobility, right? And precipitate free zones, right? There's two. What are the two mechanisms that precipitate free zones form? Well, one is that we have the excess vacancy concentration. The grain boundaries act like as natural sinks. So we are in a vacancy starved regime near the grain boundaries, right? And the other is that trace elements or other impurities can lead to heterogeneous nucleation at the grain boundary, which starves out the solute near the grain boundary, right? So you can either be a solute starved regime for precipitate free zone or a vacancy starved regime for precipitate free zone, right? And the main criteria, we need a high curvature of the solvus line. We want something that's going to precipitate homogeneously for best strength, right? And that we also want to avoid heterogeneous precipitation at grain boundaries where possible, right? Aluminum mag, remember, has spherical GP zones, right? Again, you don't need to remember too much about these. It's worthwhile remembering that aluminum zinc undergoes a spinodal decomposition there, right? Aluminum zinc mag gives us the best possible potential for H hardening, right? Again, you don't need to memorize all the phases. Aluminum lithium, the stable phase is this really complicated ordered structure, so it takes a lot to get there, right? So that has to be heterogeneous. Right, the specifics of the individual alloys is not going to be super important. What Ostwald ripening is, right, the growth of small particles, or the growth of large particles at the expense of small particles. Right, so that's basically the end of the first H hardening. For other strengthening mechanisms, right, we have solid solution strengthening. This first part is just sort of a review of what we did in strengthening, right? The difference between kinks and jogs, right, and why kinks are always mobile and jogs may be sessile, right? Especially for screw, sort of work through the geometry and make sure you get that. How dipoles are formed and why they give you a strengthening mechanism, or why they provide an obstacle to dislocations. Right. The main idea behind grain boundary strengthening is we get a dislocation pileup, which gives us a stress concentration, which can then activate another source. Right. And it's very difficult for dislocations to pass through general high angle grain boundaries. Large coarse intermetallics tend to break, tend to fracture, causes problems. Right. I'm not going to ask any specific texture stuff, but it is worthwhile knowing what texture is and how it can potentially provide strength. Right. And then this range here, right? So coarse intermetallics, half a micron up to tens of microns, right? They tend to form because of impurities, right? We can generally break them into soluble and insoluble, and they end up aligning themselves in these stringers as a result of deformation processing, right? Submicron dispersions are one size down, and these are the intermetallics that are very important because they retard recrystallization of grain growth. Right? These are the ones that give us pinning. And then the fine precipitates on the nanometer scale, this is what gives us our very high strength for age hardening. Yeah.
Getting rid of recrystallization, is that mainly a problem that we're going to see only in aluminum, or is it something if you're looking at a steel system you'd also have to?
No, in steel, there are certain steels where pinning is very important, where grain boundary pinning, right, where we want to retard grain growth. It's just in aluminum, it's a primary mechanism, right? The Hall-Peck slope is very low in aluminum. So if we want to take any advantage of grain size strengthening, we have to keep the grains very small, right? Which means that we're going to need to find a dispersion of these submicron particles to keep those grain boundaries small, right?
So that fine precipitates.
Yeah.
Like dislocations and metastable and like dissolve.
Yeah. Yeah. So the fine precipitates, I mean, that's what generally, I made the point a couple times that generally the more a alloy is reliant on age hardening for its strength, precipitation hardening for its strength, the worse its fatigue properties are going to be relative to its strength value. That's because of the cutting, right? Once you cut those precipitates and localize strain, you're done for in fatigue.
But you said that you said in the slide, it's very high strength.
It gives high strength, very high yield strength. It's difficult to cut them.
But that's still lower than peak age or the radius.
Well, I mean, if they're there by definition, it's above the critical radius, right?
Always small.
It's small, but they're still, right? They still formed, right? So they have to be bigger than R star, right? They don't have to be much bigger than R star. They have to be bigger than R star. Right. Right. So this section here is just the microstructural effects. This is the stuff that's really good to know because this is what helps you tie all those graphs back to what's happening in the microstructure. Right. Right. I spend a lot of time talking about fatigue here. And then in the specific alloys, so fatigue and work hardening. Okay. So this is very important line, right? Right here, for work hardening. Right? How many properties in aluminum can you guys think of that are directly related to its high stacking fault energy? So the low rate of work hardening, right? The ease of dynamic recovery, right? The fact that you end up with wavy slip, ease of cross slip, right? You have less effective, right? You can get around obstacles easier, right? So much of the behavior of aluminum is completely tied to its high stacking fault energy, right? So if there's a question that you don't know the answer to and you have to wildly guess, chances are high stacking fault energy will get you partial credit. Right? Okay. So in terms of specific alloys, right? The important most of this is largely informational, right? Right. I'm not going to ask questions about specific alloys, right? So you don't have to memorize compositions. General trends are good to know. That 7,000 tends to be better in toughness than 2,000. 7,000 gives you the most bang for your buck for solid solution strengthening. 2,000 is better than 7,000 in fatigue. Stress corrosion cracking is universally bad, right? And we have to do things to try and help that. Right? 6,000 is good weldability and used for extrusions. Right? So, several times the duplex heat treatments, of which this T73 temper is a really important example. Right? Back in the strengthening section, we talked about how we want to, for a lot of alloys, we'll heat shortly at a low temperature to stimulate GP zones and then go to a higher temperature. Right? So the T73 is one really critical example of that. Right? And for aluminum lithium, where the additional modulus effects come from, right? We're making a composite, right, with all these different intermetallics in there, right? And they have the intermetallics are stiffer than the aluminum, right? So overall, we end up with right. Plus, if we add solid solution effects to it. Okay. So cast aluminum alloys, generally, the microstructure is going to be significantly different than for a thermomechanically processed alloy, right? And understanding the basic ideas of what's going on in the microstructure, right? That they age very similarly, especially since they're mostly aluminum, copper, silicon. They age. The aging behavior is very similar to the wrought alloys, but we have this issue with dimensional stability, right? So being able to look at these curves and tie this back to microstructure. Why do we grow and then shrink?
Sorry, what's the parameter of dimensional
What's that?
How do you define that?
It's just
So like,
linear.
so
It's just equivalent to thermal expansion, right? Except it's not thermal. It's just how much longer has this gotten, right? And so I mean, it's not huge, right? At its peak, it's 0.05%, right? So 0.2% strain is the yield, right? Is the sort of our elastic strain limit. So it's about a quarter. The change is about a quarter of the elastic strain limit, right? Which is sort of on the order of thermal expansion, right? But you know that thermal expansion can give you pretty high stresses, right? And that fatigue in cast alloys is a problem because we have pores, and we also have large intermetallics that can break, and that the nature of the particle spacing is going to be important for fatigue. Right? So that's primarily it. Going back to the the structure, right? These, everything in here basically is stuff that just goes through the that runs through the aluminum material, right? This is sort of stuff that's important for everything. So grain boundaries, how do we describe them? Right. Energy strain field of a grain boundary energy, right? And most importantly, grain boundary surface tension, right? In terms of grain boundary energy, it's not nice and smooth. You've got these cusps that are strongly dependent on the grain boundary character. So surface tension of grain boundaries, right? Understanding why this is an unstable configuration, right? Right. Grain boundary grooving and wetting, right? These are just sort of the key things, and then the structure of the grains in 3D are not necessarily clean and pretty. Oops. That one is. And then in terms of strengthening, right, this is stuff that is just universally through there. I'd say that the key things that you really want to remember are the different mechanisms. So for modulus hardening, you've got the size, or for solid solution strengthening, you've got size interactions and modulus interactions and how they come together, right? So understanding where this comes from, right? You're not going to have to do anything quantitative, right? So if you can write the equations down if you desire for understanding, but you're not going to have to do anything with them, right? Particle strengthening, we've got coherency effects, right? Obviously, this picture is much easier to cut than this picture, right? Right, and notice the example, even though they don't say it, this looks the example that was given in the reading for cutting a coherent precipitate looks an awful lot like GP zones of copper and aluminum, even though Courtney doesn't explicitly say it. Right, you've got a modulus effect by the fact that the line tension of dislocation changes. Right, the line tension is GB squared, so you've got a energy change as the dislocation enters the precipitate. Chemical strengthening because we make a step. Right, this is not important for large precipitates, but for small precipitates it is. And our GP zones big or small? Small, right? So a step in a GP zone adds a significant fraction of the grain of the surface energy of the surface. And then order, this is not so much important in aluminum because we're mostly talking about phases that are not ordered structures, like we're, right, for the thermodynamically stable phase, like the delta phase in aluminum lithium, right, cutting that will give you an antiphase boundary. But for GP zones and theta double prime, right, this is a fairly small effect, right? This will be one of the primary effects when we get to nickel, right? And then looping around, right? And so these are, right, so think about these in terms of what they're doing in the aluminum, right? Okay, so that took a little bit longer than I was expecting, so on Wednesday I'll reserve some time for questions as well if people have any. But for like the last 10 minutes, I'll happily take any questions, right? Keeping in mind that the exam is already written, so whatever you ask is not going to alter potential questions. Yeah.
Could you explain the jogs versus kinks?
Yeah. So, so a kink, right? So when a dislocation moves, so let's just think about the slip plane, right? I've got a dislocation lying on the slip plane; it needs to move, right? There's two things that can happen, right? Two potential ways this can go. Either move the whole dislocation at once, right? Imagine if I'm in a single crystal and the dislocation runs from one end of the crystal to the other. So I've got a nice straight dislocation line, right? I can move that forward all at once, but that's hard, right? Because I've got to overcome the Peierls barrier everywhere along that dislocation line. In reality, our picture is not so clean. Most of the time, I'm in a polycrystal, I have a loop, and there's other stuff going on, right? So really only part of my dislocation overcomes the Peierls barrier, right? And what I do is then move just that part of the dislocation forward, right? That gives me a bend in my dislocation, but I haven't changed slip planes, right? So that's a kink, right? What's the penalty I pay for a kink is the energy caused by that line tension, right? I have to bend my dislocation for that to happen. But it's still much easier than moving the whole thing, right? Now I can, the rest of my dislocation can move forward by that kink moving laterally, bits and pieces of it moving forward. And most of the time you end up with like multiple steps. A jog, on the other hand, is where part of the dislocation leaves the slip plane, right? If two dislocations hit each other, interact, you're going to get a jog in one that's along the that's going to be related along the Berger's vector of another, that's going to cause that part of the dislocation to leave the slip plane. Right? Now, if it's an edge that hit a screw, right, you end up with a jog where the slip plane, right, the part that's jogged is really on another slip plane now, right? You're going here, right? You've got the situation where I've got one part of the loop is up here, one part's down here, and then I've got the jog region, which is lying on a plane, on a plane that is at an oblique angle to my two parallel slip planes. For an edge, it's not so bad because I can still move. I still have some mobility in the direction that I want to go, right? Whereas if it's a screw, the plane that I'm mobile on is now perpendicular to the original direction that my dislocation was going, right? And that causes a big hindrance, right? Yeah.
So for edges, or for screw dislocations, it would be like very immobile with the jog. But
yeah.
Can you create that same thing with an edge and a screw dislocation that interact, or is it just two screw dislocations that interact?
No, you could create it with the interaction from an edge, but well, let me think about the geometry for a second, right? Because the jog is always going to be in the direction, right, of the screw. So if you have an edge, you'll end up with out taking it, right? The Berger's vector, you'd still be in the slip plane. You'd have a dislocation line here, right? You would then be moving, have a screw component that's limited to go up and down when you were originally going. Yeah, so that would work. It's just not as easy to.
No.
It's just not quite as easy to sketch. But yeah, that would still give you an immobile part. Sorry, I had to think about that. Other questions?
The grain grooving.
The grain what?
The grain grooving experiment where you have to move the grain under the surface.
Yeah. So okay. So let me pull that up real fast. I shouldn't have closed this folder. Okay. So this is our basic relation here, right? Of the surface tension of a grain boundary. Now, so that's if all of these grain boundaries have equal energy, right? We're going to get that nice 120 degree, right? Because we want to when we want to pull. Grooving, on the other hand, we initially have a polished surface, and imagine we have a grain boundary that's perfectly perpendicular. That grain boundary is still exerting a tension, right? This has a surface tension as well, right? The free surface, and we can measure the surface tension of the free surface by ellipsometry, right? Or looking at the contact angles, put small droplets on the surface, looking at the contact angles that they make. We know the surface tension of the liquid. We know the contact angle of the liquid with the free surface, so then we can get the surface tension of that. So we still need to make our right. This is not in equilibrium, right? Because we're pulling down here. So basically, our mechanism is diffusion, right? So atoms are going to diffuse either across the surface this way, or potentially, depending on the system, it could be down the grain boundary, pipe diffusion down the grain boundary. Right, but we're going to diffuse, so now we have a net loss of material at this intersection and sort of get a hill moving away, right? But it's just the balance. You just think about it in terms of the balance of forces.
And then the other thing I wanted to ask is, in all of Bacon, they define the same equilibrium equation at a certain point as the elastic strain that you're looking at the boundary, whereas instead of surface, there's discrepancy between X and that, or is that the surface energy is the same as the boundary?
It's basically the same as the boundary tension, right? So if you look at the surface energy, right? So if we go, what goes into the surface energy equation, right? So that's the, right? It basically, right? This is the elastic effect of all of the grain bound of dislocations that make up, right? I don't like thinking about general grain boundaries in terms of the strain, because I think in terms of the strain field of the dislocations, because it really only makes sense for low angle grain boundaries where you've got nice planar arrays of dislocations. As soon as you have a general high angle grain boundary, thinking about the individual dislocation structure of that grain boundary doesn't make sense anymore. So it's better, just easier just to think of it as a generalized surface energy or a surface tension. Right. And we know the grain boundary doesn't exhibit a long-range elastic field. Right. So the number of problems you can get at by thinking about it from the elastic, an elastic strain is fairly minimal. Okay, so if I confused you enough? Okay, so if you have any other questions, we'll take some time on Wednesday. And then on Wednesday, we'll do a very brief introduction to the iron-carbon phase diagram. Right?